Okay, great. All right, so I think Ed gave a great big picture talk. I'm going to give a very small picture talk, but it's also about predicting the future, just in a very different way. So I'm not going to talk about robotics today. I'm going to talk about reinforcement learning for LLMs. There we go. Okay, so an LLM agent obviously interacts with some kind of environment. Typically, this would be some set of tools, some kind of resources that it can use. But we might also want our LLM agents to interact with people or interact with physical systems. Maybe it's actually issuing commands to a smart home or something like that. Some kind of system that's not so easy to simulate. And we want to do a few things. We want to optimize for good outcomes. We want to optimize to get high reward. That's what reinforcement learning is really good for. And of course, we've seen an explosion of research on reinforcement learning for agents. But we also want to handle real-world dynamics, systems that are not just predictable API calls, but unpredictable, messy things like placing that phone call that Ed showed in his talk. So here's a running example that I'm going to use in my presentation. This is kind of a benchmark task. It's from a paper by Wong et al. Called Persuasion for Good. Here, the agent is supposed to be persuading a person to donate to charity. Obviously, it's a benchmark task. It's not something that we necessarily actually want LLM agents to do, but it's an interesting scenario to consider that you can think of implicating many of the phenomena we might expect when, for example, an LLM agent is interacting with a customer, placing a phone call, or trying to interact with a user who's making a very complex request. You have to think about their thought processes. You have to figure out where they're going. Are they skeptical? Are they persuaded? Are they happy? Are they angry? Are they getting frustrated? So this is a very complex kind of domain. And of course, ordinarily, if we were to train LLM agents with reinforcement learning, we would want to heavily use simulation. And that's straightforward to do if you're training agents to make API calls or use tools, but it's not so straightforward when you want to interact with people, interact with physical systems, interact with messy aspects of the real world that are hard to model. So what about, instead of trying to simulate environments so that we can run reinforcement learning for our agents, what if we can somehow leverage the LLM itself? The LLM should be very good at predicting things about the world, especially when it comes to people's behavior, because of how it's trained. LLMs are literally trained to predict which buttons people will press on keyboards. So you would expect that a model trained in this way should be very good at predicting what buttons people will press on keyboards, or what words they'll say, or how they'll behave in the future. So let's try to think about how we can leverage that. Let's go back to our little donation persuasion example. Let's say that our agent observes the person saying this line. Well, inside of that LLM, there are representations, and those representations are actually very good. They're representations of what the model deduces about this interaction. And those representations could be very useful, but they're not by themselves a great basis on which to make decisions, because you don't just need to deduce something about what happened, you need to predict what will happen in the future, not just to make a great investment, as Ed told us, but actually to figure out how to achieve your goal in this dialogue situation. So you need something more. You need to look at these features, introspect them, understand what's going on, and then use them as a basis for predictions. So that other thing that you need, which you'll use to build a really great predictive model of this interaction, is basically domain experience. You need to know a thing or two about persuading people or talking to customers or helping users in order to build a predictive model of this particular situation on the basis of the representations that your LLM has from all that large web scale data. Now, critically, that prior experience does not need to be experience of optimal behavior. So the key thing I'm going to talk about, which is enabled by leveraging reinforcement learning in the right way, is to use in-domain suboptimal experience, which could come, for example, from people talking to other people, which allows you to understand what might happen, and then leverage that knowledge to figure out how to act so the thing you want to happen actually happens. So the key idea is to analyze suboptimal prior data of human-human interaction to understand how people react to one another, and then using it to build powerful predictive models of behavior on top of these LLM representations. And crucially, we will not be using the prior experience to understand what the agent should do, but rather what might happen, such that we can then plan for the outcomes we want. Okay, so what do we need to predict an optimal strategy? This is the kind of question that we're going to train our model to answer. If I am in this situation, and I take this strategy, what will happen in the future? So you might predict that if you take strategy A, then the outcome is the user distrusts us. If you take strategy B, the outcome is the user is bored. If you take strategy C, the outcome is the user is interested in your charity. Okay, so if you're trying to get them to donate to charity, pick that one, right? That's the good one. So if you can answer these kinds of questions in a very flexible way, that's a really great basis to get your agent to behave more optimally. So how can we formalize this problem? Well, the yellow thing is the outcome, and what you really want to predict is the probability of an outcome given the situation and the strategy. So in the parlance of reinforcement learning, this is the state, this is the action, and this is a goal. And we're going to train these kinds of models to predict the probabilities of many different goals and then leverage them in a decision-making framework. Okay, so this needs to be learned from domain-specific data, and it has to be a long horizon prediction. What will happen if I pursue this strategy for an extended period? What will happen at the end of a long interaction? So this is called the goal condition value function. And actually, classic reinforcement learning gives us really great tools for training these things. I won't throw lots of math at you. This is actually the only equation I have in the slide, and I'll walk you through it. So if you want to learn P of G given SA, it's actually described by a Bellman recurrence, which makes it really convenient to learn from suboptimal data. Basically, that probability is equal to the probability that you've reached the goal already. That's the easy one. But then if you haven't reached it already, then it's the probability that you'll reach it in the future. And that's a recursion. Basically, go to the next time step and see how likely are you to reach it from the next time step if you select the best possible action you can at the next time step. So it's taking into account the counterfactual property that you will be acting to maximize the probability of this outcome. And this is why you do not need optimal data to train these things. The data tells you what might happen, what kind of transition might occur, and then you will ask, well, if I then act optimally, how likely am I to achieve this outcome? So that's why we don't need optimal data, and this is basically just Q-learning rebranded and repackaged in a slightly different way. Okay, and we can, of course, train for many goals at the same time. So how does this work in practice? Well, we take our data set. So we're going to, if we're doing this persuasion task, we're going to take the persuasion for good data set from Wong et al.'s paper. And that has people talking to other people. In every one of these conversations, we'll pull out some time step and treat that as the state. We'll look at what the other person did next. We'll ask our LLM to kind of pretend that you were that person. What strategy are they doing? And it will say, oh, it's executing the strategy. I should explain I want to donate. Okay, that's an action. And then we'll look into the future of that conversation in our data set, and we'll find some outcome. Maybe at the end of this one, the user wants to donate $0.3. So that's the outcome. The goal can also come from other conversations. It doesn't have to be the outcome that was actually achieved in that conversation. But it should be something that's kind of sensible in the context of the task. And using these, we'll construct a data set. The data set just consists of tuples state, action, next state, and outcome, where the action and the outcome are obtained via summarization, and the state and next state are literally just the prefixes of the conversation at that point. And this data set then we can plug into an offline Q-learning algorithm. We're going to use the representations inside the LLM as the features for this. That's very convenient because the LLM already can take these states and represent them in a way that's fairly sensible. And then on top of that, we can actually train a very small model using this Bellman recurrence to represent these goal condition value functions. So we run offline RL to train goal condition value functions and then leverage the representations as features on top of which to train these things. Now, once we've trained these predictors, we can leverage them in a decision-making loop, which is very similar to self-refinement. So at test time, when the agent is actually talking to a person, we're going to ask it to propose some relevant outcomes that it might care about. So this is just like, make up some things that are important in the context of this task. Maybe it's important to figure out if the user will feel threatened or if the user trusts us more. Like, these are the things we should care about. Propose some initial strategy, maybe a bad one, like argue with the user. And then predict how likely each of these outcomes are using that bank of goal condition value functions we trained. And now you can take that information, you can give it back to the LLM and tell it, like, hey, this is what I think will happen if you follow this strategy. Based on this, refine your strategy to be better. And you can perform the self-refinement loop multiple times. So we're not just blindly following the optimal prediction, we're actually plugging this into a kind of a planning process, but now it's a planning process informed by what you've learned from that in-domain data about long horizon prediction. Just to show you at the end how this actually plays out in practice, here's that persuasion task. Here, the donor is clearly skeptical. I think it's a waste of money. The agent has some thoughts. Initially, it says, oh, maybe my initial strategy should be I should talk about the accomplishments of the charity. It evaluates the possible outcomes of that strategy, determines that that's a bad idea, refines it, and then says, oh, I should address their skepticism and share financial accountability reports. And this refinement can be done multiple times. Here's another benchmark task. This is the social deduction game Avalon. For those of you that have played the party game Mafia, it's kind of like that. So there's like a group of players that are playing together, but one of them is like secretly the bad guy, and you have to figure out who it is. So you have to really pay attention to the interactions. And here, too, the agent has some thoughts. It says, oh, I believe the quest will fail because player 2 is the minion, like that's the bad guy. Proposes a bunch of possible outcomes, evaluates their probabilities, and then comes up with a better strategy that could allow them to win the game. So this works quite well in a bunch of benchmark tasks. We actually intentionally chose benchmarks that span the range of different challenges. So web shop is a more traditional kind of tool use AI assistant task, whereas persuasion is much more of like a task that requires understanding human psychology. Avalon requires understanding social dynamics. And across these benchmark tasks, this method actually does quite a bit better even than methods that are actually designed for these benchmarks in mind. Now, this is kind of a deep dive on a very specific technical idea. The main thought I want to leave you with at the end is that when we build LLM agents, we should really think deeply about how we can use suboptimal data of the kind of interactions that are easy to get to deduce more optimal strategies. And I think reinforcement learning can be a really powerful tool for that. LLMs know a lot about the world, and we can use them to make predictions that aid in decision making. In-domain data can help us, even if it's suboptimal data. Offline RL can help us learn more optimal behaviors, and we can combine all this to train agents using only suboptimal data that could outperform the humans that generated the data in the first place. Thank you very much.